This is the investigation for in properties of curves, which is actually the third differentiation chapter of the book. I think there's one more. I am going to focus on a real-life example. I got to know this water slide every time I would go back to Kansas to visit my parents several years ago, when they would take me to the airport and drive me from the airport. We would always go by this huge tower of a water slide, which was said to be I think like the tallest water slide in America at the time. This water slide had a tragic story. I think on maybe the first day it was open, but like very soon after this water park opened, a boy died on the water slide, suffered a terrible accident. And basically because of that, the whole thing shut down, and that was the end of the water slide. That was the end of the water park. So it was a very tragic story. At the end of this investigation, we'll talk about why that accident happened, and maybe how your analysis could even show where it might have happened. Okay? All right. So there is a profile view of the water slide right here. I extended it a little bit here where it says G and H, just so that we could get some more interesting curves out of it. Okay, but it has plenty of interesting curves as it is. It says first, with a highlighter, draw tangent lines at the points A, C, E, and G in the photo above, and estimate the gradients of these tangent lines and write them here. Okay, so you guys already know what tangent lines are. They are straight lines which hug the shape of the curve at the points they cross. And tangent lines only touch the curve at one point. So it says to draw them at A, C, E, and G. And it says to use a highlighter, so I'm going to use a highlighter here. Actually, I'm going to make the highlighter a little bit less thick. Okay, and it says A, C, E, and G. I'm going to draw tangent lines at A, C, E, and G. So let's look at C first, because that's kind of an easy one. There's the point I'm trying to draw it through. I want the straight line to hug the curve. It would basically look like that, right? What about at E? There's the point E. I want it to hug the curve. I'm going to have to change the color. Okay, what about at G? What about at A? Do you see a pattern happening here? So when I draw all the tangent lines, they all have a similar characteristics, which is that their slope or their gradient is flat, also known as 0, right? Right, with a highlighter, draw tangent lines at B, C, D, F, and H. Okay, so let's change it to green here. B, D, F, and H. So B, you can see, is kind of slanted like that, right? B. D is kind of like that. F is kind of like that. And H is kind of like that, right? Okay. Estimate the gradients of these tangent lines and write them here. Now you might say, how am I supposed to estimate the gradient of these tangent lines? Well, just draw a little triangle. And this triangle looks a little taller than it is wide. And would you say it's a positive or negative slope? Negative, right? Because it's going down. So I would say it would be like negative 2 down, 1 across, so negative 2 about. So for B, I would say negative 2. What about for D? let's see, D looks like a positive slope. It's about 2 across, 1 up, so that would be 1 over 2. So I'd say D is 1/2. And F looks like it's going down. It looks like about a 45-degree angle, right? So that would be about a -1 slope. Finally, H. H looks very steep. Maybe it's going 3 down, 1 over. So that would be about a -3, maybe. Okay? All right. For graph 1, this is the gradient graph. And what we're going to do is we're going to take all these values that we wrote values down for. And so I'm going to just write them for our convenience. I'm going to write them directly below. So this is 0. B was -2. C was 0. D was 1/2. E was 0. F was -1. G was 0. And H was -3, right? So what I'm going to do is I'm going to graph these values on this scale here. If you remember, we did something similar in chapter 14, which we did last December. We graphed for the mosaic the mosaics that we created for the quadratic and for the cubic, we graphed the gradient values, the red values that were written on the tiles. And we're doing the same thing here. So I'm going to graph, let's see. First I'm going to graph 0 at A. Then I'm going to graph -2 at B. Then 0 at C. And 1/2 at D. And 0 at E. And -1 at F. And 0 at G. And -3 at H. Okay? Then I am going to connect them with a smooth curve. Okay. It says graph 2 here, but it's graph 1, right? Okay. So graphing them with a smooth curve means that you just make a minimum number of undulations and still go through all the points. Okay, that didn't come out very well. Okay, something like that. All right. Graph 2, rate of change in the gradient. Now with graph 1, repeat the process. Draw tangent lines at A, B, C, D, and H and estimate the gradients at each point. Your estimate will be rough, but should be correctly 0, positive, or negative. Plot the points and connect them with a smooth curve in graph 2 below. Okay, so now I'm going to use the highlighter. And I'm going to maybe I'll color code it. So I'll put yellow for the 0 slopes. Oh, this is maybe a little bit too thin. 0, 0, 0, and 0. And then I will use green for the positive slopes. Green. And that's it. And then I'll use red for the negative slopes. Red, red, red. Okay. And then I will write down my estimates for the slopes. So these yellow slopes, of course, are all slope 0 because they're flat. The red slopes, of course, are all negative, but like this E one is less negative than the others. Let's say the E is like going 2 across, 1 down. That would be negative 1/2. What about H? H looks about like maybe negative 1, 1. It's about like 45 degrees, maybe closer to 30, 60, 90. Negative 1 is okay. Okay, for H. And then A is a little bit steeper. We'll put negative 2 for A, okay? All right. Now, oh, and C. C is the green one. That looks like maybe positive 1, maybe 1/2. We'll say 1/2. Oops. One half. Okay? Now we're going to graph all of these slopes in graph 2. So I'm going to draw my axis again, and I will draw my curve. So A is negative 2, B is 0, C is 1/2, D is 0, E is negative 1/2, F is 0, G is also 0, and H is negative 1. Okay? So I'm going to connect these with a smooth curve. Okay, about like that, right? All right, let's see what we do next. On which points of the waterslide track could you carefully or not so carefully balance a ball so that it would stay in one place without rolling away? Okay, so let's go back to the waterslide track. Where could I precariously balance a ball that it might not roll away? Okay, so those would be the places where it's basically flat, right? So it would be A, F, G, and C, right? All the places where we said that the gradient would be 0 are places where you could precariously balance a ball just for a second, okay? So that would be A, C, E, and G. A, C, E, and G. Oops, that's very messy. Write down the gradients for these points. It's 0. We already talked about that before, but it's just a different way of looking at it. The points which have gradient 0 on a curve are places where they're momentarily horizontal. Okay? At the tops of these hills and at the bottoms of the valleys, that's where they have slope 0. Classify each point into a local minimum, local maximum, or stationary inflection point. Okay, so what do we mean by local minimum and local maximum? Well, think back to quadratics. Okay, the vertex of a quadratic is either going to be a local minimum or a local maximum. In fact, it's a global minimum or global maximum because all the other points of the quadratic are higher or lower. What if you have a cubic? With a cubic, now we can kind of see why they say local minimum and local maximum. This is a local minimum because there's points over here which are lower than this point. So it's definitely not a global minimum. It's a local minimum. Okay? Just around its own neighborhood, it is the lowest point. And a global maximum, same thing. Over here, you have points that are higher than this point, but around its own neighborhood, it is the maximum. That's what we mean by local minimum, local maximum. So you can see that local maximums, we have A and E, for example. A and E are the tallest points in their local neighborhood. Okay? So A and E are maximums. A and E are maximums. What about minimums? It would be C. Was G a local minimum? No, because look, like looking at the left side of G, it goes up, so it kind of looks like a minimum, but we look at the right side, it's just going down, so it looks like a maximum on the right side. That's what's known as a stationary inflection point. A stationary inflection point is a place where the curvature changes from curving this way to curving this way. So the minimums is just C, and then stationary inflection point would be G. So let's write those down. So AE is maximums. C is minimum. And G is stationary inflection point. Okay? B, D, and F are inflection points, but not stationary ones. What is similar between B, D, and F are inflection points, but not stationary ones? What is similar between B, D, and F and the stationary inflection point you just found? Okay, so the stationary inflection point, I'm going to erase some of these highlights because it's kind of hard to see what's going on, right? Okay, so the stationary inflection point we're talking about is G. Do you see how starting from G, there's a part that kind of goes down and there's a part that goes up? Okay, it changes the way you're turning. Imagine if you're a car driving down this curvy road. The stationary inflection point is the point where you exactly have the steering wheel pointed toward the straight, right? Here, the green part you're turning left, the red part you're turning right, but in between there's a place where the steering wheel momentarily passes through 12 o'clock. Okay? And with B, D, and F, that change in curvature happens also. Do you see? B, D, and F. It happens in all three places. What is the difference between BDF and G? G is special because it's not just an inflection point. It's a stationary inflection point. Stationary means it doesn't move. And what is it about this inflection point that looks like something doesn't move? It's the ball, right? Remember, if you put a ball at the maximum min point or the stationary inflection point, it will momentarily stay in the same place before maybe it gets jostled and rolls away. So if you look at B, D, and F, those are its slopes, right? So even though they're similar to G in that they change curving direction, they are not stationary points where you can place a ball and it won't roll away immediately. Okay? So that is the difference between a stationary inflection point and an inflection point. So the curve direction switches, right? From like you have the steering wheel to the left and then you change it to the right. That's the inflection point. What is different? The difference is that the slope is not zero for B, D, and F, right? You have several local minimums, maximums, and minimums, but which part of the water slide would you say is the global maximum and minimum? Okay, so global maximum is pretty easy, right? A is not only a local minimum, it's also a global maximum. It's not only a local maximum, it's also a global maximum because look, it's the tallest point on the water slide. That is the record-setting point which made it the tallest water slide in America. Okay, so A is a global maximum. So where's the global minimum? Well, if we look at the local minimums, there's C, and that's the only local minimum. Is C the global minimum? It would be, maybe, except for there's also this extension that I drew on it. I drew G and H and this guy falling into I, right? So actually, the lowest point on the water slide is actually I, right? But you're like, oh, but I is not a local minimum or local maximum because it doesn't have the momentary place where the slope is zero, right? Local minimums and local maximums have these characteristic tangent line slopes. I does not, okay? But that's the thing. When you find global maximum and global minimums, you're not necessarily looking for places where you have stationary points or momentarily the tangent line slope becomes zero. You're looking for the lowest possible point, the highest possible point. So whenever you do this with a curve, you need to look at the endpoints of the curve. The endpoints of the curve are here and here. These are also possible candidates for being global maximum, global minimums. In the case of I, it is the global minimum. So I is a global minimum. Okay? All right. Comment on if you feel lighter or heavier than normal in each of the intervals as you ride the water slide. Okay. So you guys have a lot of experience riding elevators, riding in cars when you're going up and down hills, riding on water slides and roller coasters. When you look at the path of this roller coaster, where would you feel like you are very light and you are coming off the slide? Have you ever felt like that on a roller coaster? Where do you feel like you're very heavy and you're being pushed deeper into the water slide? Okay? So I want you to think about that for a second. And then we'll mark those, okay? So where you feel light, I'm going to use blue. And where you feel heavy, I'm going to use red. Okay. Okay, so think back to your roller coaster experiences. You're at A. You're starting out. The car is just about to tip over the edge of the first downhill. That moment when it tips over, do you feel light or heavy? It's like when you kind of like lose your breath. You feel light, right? And then as you pass this inflection point, don't you feel driven down into your seat? You feel like there's more gravity force on you. They call that G's. And then when you pop over the top of the hill, you kind of feel light again, right? And then as you slow down here, because it's getting flatter, you feel slightly heavier. And then as you tip over the edge, it's just like when you tip over that first edge, all of a sudden you feel lighter again. Okay? So let's mark A through B is lighter. Oops. A through B is lighter. Hey, come on. Come on, blue. D through E is lighter, and G through H is lighter. And B to D is heavier, and F through G is heavier. Okay? Check graph 2 and see which intervals, positive values, concave upwards. Let's check. Concave upwards. Negative values, concave downwards, correspond to feeling lighter, heavier. So A through B is lighter. A through B. So A through B is a negative region, right? A through B is negative. D through F is negative. B through D is positive. And F through G is positive. G through H is negative. So looks like the light regions correspond to negative and the heavy regions correspond to positive, don't they? Positive corresponds to H. So basically, the light regions correspond to negative values in graph 2. The heavy regions correspond to positive values in graph 2. Negative corresponds to places where the original curve is concave down. Do you see the blue parts of the curve? It's like cupped down. The red parts of the curve are cupped up. Cupped up corresponds to positive concavity. Cup down corresponds to negative concavity. I kind of remember that by saying, oh, cupped up, positive, cupped down, negative. I draw this little picture here. Okay? So looking at the original curve, we can see that when we have graph to positive, it's when it bends up. And when we have graph to negative, it's when we bend down. And if you think about it, the reason why is because look at the blue part. The blue part, you have a slope that's like this, but then you have a slope that's like this, and then you have a slope like this. You can see that the slope gradually gets steeper and steeper, right? And do you see how it makes a cupped down shape? When the slope is rotating to the right, like it goes like this, and then it goes like this, it's making a cupped down shape. The slope is steadily getting more and more negative, right? Here it's positive, then it becomes 0, and then it becomes negative. So when the thing is like getting more and more negative, it goes from positive 1 to negative 1, it's getting more and more negative. That is a negative change in slope. That makes a concave down shape. And vice versa. The red is just the opposite. As the slope transitions from being negative to starting to be positive, that's a positive change, right? The positive change was what makes the cupped up shape, the red parts of the curve. Okay? That'll become more intuitive as it goes along, and you're going to figure out ways to remember that. But basically, you can actually identify parts of the roller coaster or the water slide where the concavity is up or down by the feeling that you have. The feelings that you have when you feel your body being pushed down into the track or like it's floating above the track. Okay? So those feelings actually indicate the concavity. If you have a roller coaster that's perfectly straight, you don't have those feelings which make roller coasters exciting. You have to have the concavity. Okay? This part here is kind of just an aside, okay? Especially for those of you who are taking physics right now. This is something that you've worked with before, and it's something that appears in math also, which is normal lines, okay? Normal lines you've used in physics, usually kind of in a boring way, because usually in physics you do problems where you have straight slopes. And when I say slope here, I don't mean the math slope. I mean like a wooden platform slope. When you have these slopes, you draw gravity force diagram things, and when you draw the force diagrams, you usually have something called the normal force, and the normal force is executed on the block directly perpendicular from the wooden triangle here. And so this normal force is called the normal force because normal is another way of saying perpendicular in math. It's the 3D way of saying perpendicular, because perpendicular, we often talk about perpendicular when we talk about 2D. Usually when we talk about 3D, we say normal. So in this particular case, we just want to draw the normal lines that are going through each one of these letters, and I'll do that in green here. And so basically the normal line is perpendicular to the tangent line. So I'm just going to quickly draw all the tangent lines that we drew before in order to make it easier to draw the normal line. And the normal line, let's use, I don't know, black. The normal line is just perpendicular to that. So you just draw the normal lines perpendicular to these green lines I just drew. Okay? And that was just to introduce the concept of a normal line, which is like a tangent line, except it's perpendicular to the tangent line. It actually goes through the same point as the tangent line. It's just perpendicular to it instead of following along the direction of the curve, it goes totally opposite. It's 90 degrees to the direction. Okay, I forgot to tell you the most important thing. I was just about to upload this video, and then I remembered that I promised to tell you about the accident, and we didn't talk about the accident, right? So what happened to this poor boy was that, he ended up flying off the raft, and they had put some kind of I don't know if it was like a little roof to shade the people from the sun, or maybe it was a sign. I'm not sure it was, but it was some kind of overhang on part of this water slide. And since he flew up from the raft, he hit the overhang, and it killed him. So you can kind of imagine, knowing what we know about our intuition on roller coasters and our analysis of these curved tracks, you can kind of imagine where this overhang was and where the boy ended up being killed, right? Because we know that in the blue sections is when you feel light on the curves, and when that feeling of lightness gets too great, guess what happens? Your body actually leaves the track. Have you ever felt yourself leaving the seat of a roller coaster? Well, if you're not seat belted in the roller coaster and your body starts feeling light, eventually it's, the roller coaster goes down and you're not in it anymore. And that's exactly what happened in this case. So you can guess that it was probably around point E, right? Point E is probably the place in this roller coaster where you really start coming off the track. And basically the cause of the accident was that they had made calculations of, what would happen based on people's sizes. And somebody who was too small for the ride went on it, and the people who were responsible for checking didn't check well enough, and that led to the accident. So yeah, terrible. This was called the Schlitterbahn, and I'm not going to say here exactly what happened in the accident, but if you go look up the articles, you can find out exactly what happened. It's a terrible incident. Okay? All right. Well, that was it for the investigation. Sorry to end on a downer. Shouldn't have occurred. And that's it. That's it for this investigation.